then becomes, how do we translate this extremely abstract model from mathematics into molecular communication? Well, let's review a few ways in which we might wish to transmit a message. So for example, I present to you here a binary message. So I can basically collect the set of all possible messages. Let's express them as binary vectors, and perhaps this is 1. So in other words, I wish to transmit a 1, 0, 1, 1, and so on. So basically I want to convey this using molecular communication. How might I do that? So to send a 0, I might do the following. I might send with quantity. So in other words, what I'm going to do is I'm going to describe a few strategies by which to send zeros and by which to send 1s and how to distinguish between them. So basically what I'm talking about now is how the transmitter operates and how the receiver operates. So if I want to send a 0 and I want to do it using the quantity of molecules, perhaps I will release no molecules. And if I want to send a 1, perhaps I will release lots of molecules. And then what the receiver will do is it'll count the number that arrive. So obviously we can see that if no molecules were sent, no molecules will arrive. If some molecules are sent, then some number greater than or equal to 0 of molecules will arrive. If I see something, then I can obviously decide a 1. If I see nothing, it might be that a 0 was sent, or it might be that a 1 was sent. Let's suppose I use a different method, perhaps I can use identity. So in other words, in order to send a 0, I can release a molecule of type A. And in order to send a 1, I might release a molecule of type B. And then the job of the receiver is to measure the identity of the arrivals and figure out exactly what was sent. So in this case, we can say that a 1 was sent because that molecule, the type B molecule arrived. So this is fallible. The molecule might get lost. As I'm going to describe a little later, molecules might arrive out of order, which is actually a pretty serious problem. The third way that we might communicate using molecules, we might use timing. So one thing I can do is I can send a 0. In order to send a 0, I can release a molecule now. In order to send a 1, I wait a certain amount of time, and then I release a molecule later. So what the receiver will do is it will measure the arrival time. And if it's early, if the arrival is early, then it will decide a 0, and if the arrival is late, then it will probably decide a 1. Now the issue here is that the propagation time from cell to cell is random. So therefore, it might be that I released a molecule early, and it takes an unusually long time to propagate, and then it arrives late, so I decide the wrong thing. So what I'm going to do is I'm going to boil these sort of first glance or first approach ideas for sending information across this channel, and I'm going to boil it down to what I call an ideal system model. So my basic problem is that I'm an electrical engineer by training. I'm not a biologist, so it's most helpful for me to abstract away the details that I don't necessarily know about. The other issue is I want to abstract away details that might be different from system to system so that I can say something in general about all systems. So what I'm going to do is I'm going to take this communication system that we've been talking about and try to boil it down to the most simple possible arrangement so that I can actually say something about it mathematically. So while I say this, it's important to keep the following in mind. All models are wrong, but some are useful. So this is not necessarily a correct model that I'm about to present to you as far as the physically correct way in which cells communicate with each other. But what I am trying to do is I'm trying to build a model that does two things. Firstly, it captures at least some of the physical reality of what's going on. And secondly, that we can say something about information theoretically that is useful and that is generally applicable.
So this is always molecular communication,
yes.
And it somehow propagates in this diffusing medium, basically.
That's correct. So, and in particular, when I talk about the physical realisticness, I guess, of the system, that's the part that I really want to capture, is the fact that that the messages are being conveyed through diffusion. Okay, so we come back here. This is the model that I talked about, and really what I'm interested in. What we often do in communications is we assume transmitters and receivers are ideal. In other words, we're not really concerned about either the complexity of these devices or how to implement them. So that's one thing that I'm going to do. Another thing that I'm going to do is I'm going to try to find a nice mathematical model for the channel itself. In other words, the way in which those molecules propagate. And in particular, my objective is the following. So when I derive an ideal system model, this is really the question that I'm asking. What is the best you can do? And this is the question that we ask in information theory. So what is the best you can do? If you've ever taken a course in information theory, you know that this is the answer. This is called the mutual information, this quantity right here, and it's related to these two expressions, which are called entropies. So the notation here, Y, is the output of the channel, and X is the input. So in other words, X, you pick the message that you're going to transmit, and Y is what you get out of the channel at the other end. This is the entropy of the channel outputs minus the conditional entropy of the outputs given what you send. So in other words, if you know what you send, what's the uncertainty in the output? This is just plain the uncertainty in the output, treating the input as a random variable. And we know that this quantity, if I specify exactly what strategy I'm using for the inputs, this quantity gives me the maximum rate at which I can transmit reliably across the channel. This is Shannon's channel coding theorem that showed this. Whatever number you get here, you can't go faster than that and still achieve reliable communication. So because the strategy is up to us, we can pick whatever strategy we wish to use across this channel. We can maximize over all possible strategies. So that's the notation here. If I take the maximum over this is the probability distribution function of the inputs over the mutual information. That gives me this quantity C, and C is called the capacity. So this is the absolute best that you can possibly do, maximized over all possible strategies that you can use. So this is my objective here. The question that I want to ask is, what is the best you can do with diffusion-mediated communication? What I want to do in order to solve this is I want to figure out, probabilistically, how do the inputs and outputs relate to each other. So this is, while abstracting away the details of the transmitter and the receiver. So this is basically my approach. And then finally, what I want to know is I want to know something about C. So in this talk, I won't calculate C, but what I will do is I'll present some ways to bound C. I will present some of the difficulties in calculating C, and I will give you my best guess as to what C probably is. So here are the system assumptions that I'm going to make, and you'll immediately see that they're ridiculously unrealistic. Firstly, transmitter and receiver are perfectly synchronized. In other words, the transmitter and receiver share a clock, and they're going to agree on some common time base with perfect accuracy. Again, this is a common assumption in information theory, and it's not such a bad assumption. It's not a great assumption, but it's not such a bad assumption in computer communications, because computers can obviously share clocks. Those clocks can drift, so this is obviously not a perfect assumption. In biology, it's probably less true, but it's a familiar assumption as far as information theorists are concerned, so let's use it. And it also makes things easy. Second assumption. Transmitter perfectly controls the release times and physical states of the transmitted particles. So in other words, what I'm saying is the transmitter does anything you want it to do and does it perfectly. Thirdly, receiver perfectly measures the arrival time and physical states of any particles that cross the boundary. So in other words, again, the receiver does anything you want it to do and does it perfectly. And fourthly, the receiver immediately absorbs and removes from the system any particle that crosses the boundary. So you don't get, in other words, you never see the same particle twice with the receiver. So it should be clear that the first three assumptions are basically everything is perfect. And this fourth assumption is a little bit different, but shortly we'll show that this assumption is ideal. But what I want to explore is what are the consequences of this. So this is the basic physical setup we have. I assume that the transmitter is a point right here. I assume that the receiver is an infinite line over here, located distance d away from the transmitter. And what will happen is I'm going to drop particles down into the solution, and they will propagate via Brownian motion until they hit the receiver. Now remember my assumptions. I can perfectly control at the transmitter. I can perfectly measure at the receiver. And as soon as they hit, they're gone.
So the particle will eventually be absorbed?
In this scenario, yes. If you assume no drift, probability 1, the particle will arrive. The only scenario in 2 dimensions when this doesn't happen is if there's a drift in this direction, but I've never considered that in my work.
Well, that's a model for, a married couple after about 10 minutes.
Yes.
They're not trying to communicate, and so
That's right, and so they're drifting.
messages are going.
That's right, that's right.
It gets better after 55 years.
I'm glad to hear that.
That's right.
Should have
From
started earlier
experience.
then.
Anyway, the takeaway message here is that the way in which I've set up this scenario, the only uncertainty in this system is the propagation time. So in other words, everything is certain up to the point where I drop the molecule in. Once it arrives, everything is certain, and the only thing that I really need to worry about is how much time it takes from transmitter to receiver.
Does the location vertically matter when it's received?
No,
In
in
this
fact,
case?
Actually, good question.
Because then you could ignore the vertical component.
Yeah.
What I include the vertical component for ease of visualization, but in fact, what I mostly study is one-dimensional.
Okay, sure.
One-dimensional Brownian motion, but that's pretty hard to put on a slide and make a nice twirly thing like this. Because this is basically the universal standard for Brownian motion. Some kind of twirly thing like that.
That's a very smooth trajectory.
I know, I splined it. Anyway. So here's what I'm going to prove to you. Here's your first theorem. And this is another good reason to use these modeling assumptions. So they're very unrealistic, but my theorem is that mutual information is higher using these assumptions than if you abandon any of them. So in other words, the reason why I call this the ideal system model is that it's information theoretically ideal. If you ignore any of these assumptions, your mutual information goes down. So in other words, I'm upper bounding the maximum possible mutual information of any such system. So it should be obvious that basically assumptions 1, 2, and 3 are perfect assumptions. In other words, everything is perfect, everything's measured perfectly, everything's manipulated perfectly. So I think it's obvious that those first 3 assumptions are ideal. The fourth is a little less obvious, but in fact it falls out immediately as a property of Brownian motion. So let's go back here. Here's my Brownian motion from the transmitter to the receiver. Now, let's suppose I did the following. Let's suppose I ignored the fourth assumption and I allowed that particle to continue propagating. So this is actually quite a bummer analytically, because that particle comes back and comes back and comes back and comes back, and you see that particle over and over, and you can't distinguish necessarily the additional arrivals from the first arrival, and secondly, eventually your system will get bunged up by, if you keep doing this for infinite time, which is what information theorists like to do, eventually there will be, this entire system will be completely bunged up by molecules. And those...
Probably it's not realistic for biological system. Usually the cell something binds to receptor or whatever, and then after.
Precisely. So in fact, since I've developed this model, I've learned that it's actually not unrealistic physically, that in fact cells do absorb those molecules and can remove them.